Let's talk about the center of mass and why it's important. Well, the first thing, it's what we've looked at all along. If you don't believe me, just look at a force diagram. We've been talking about all the forces acting at this little point right here. And I'm going to tell you that this little point that we've been contemplating is the center of mass. So now we're in an area where things can spin. So we've got this rogue capybara, and it's going to charge, and that person's going and going and going. And if you looked, that person rotated around this spot right here, or the person's center of mass. But how do we get this? Well, we've got a system, let's say, and this system has two objects, two spheres, because that's what we're going to use right now, and we're going to rotate. So we find the moment of inertia. Now we know that this moment of inertia, if you know that k rotational is equal to 1 over half I omega squared, if you want to minimize k rotational, you can also minimize the inertia. Remember, all we're looking at is minimizing the energy, and systems like to minimize energy. So let's take a look. We want to minimize the moment of inertia. Let's express this. We can figure out that RA and RB are related because I know this distance L. So I just relate RB to RA. Now there's only one thing to worry about. We'll take the derivative. Again, we want to take the derivative because we want to find the minimum k rotational. So what we're going to do with this, take the derivative with respect to RA, and we get MRA. Let's solve for the location of A, this position. Remember, R is position. So this right here, that's the total mass of the system. Well, this up here is a weighted average. So this center, RA, since MB is bigger than A, B is larger than A, it's farther away. Which means the center is going to be closer to B, which is what you'd expect, because B is larger. If you were trying to balance this, imagine trying to put your finger on somewhere. We'll talk about in the next video where the point that balances is your center of mass. So let's put a definition to it. It's the mass-weighted center of the system. The smallest moment of inertia occurs for rotations about the center of mass. And any freely rotating object, like that person who got legs taken out by a capybara, rotates around the center of mass. So let's look at the mathematics. Mass-weighted, we're going to add up all the masses at their positions, because now where the mass is located matters, just like in moment of inertia. And this is just the total mass of the system. If you have two directions, remember this R right here is a vector, which means we can break it into components. We can get an x center mass and a y center mass for rotations about the x and y axis, respectively. Or if we want to go into integral form, these sums just become integrals. And notice you're integrating around every little piece of mass. Looking at this example, I've got three terms. Let's go ahead and start in the x direction. Again, on the bottom I have total mass, and these are the mass-weighted distances for the x position. So I just add this up. Mass 1, x1, mass 2, x2, mass 3, x3. We plug in our coordinates using these little x positions right here. Total mass again on bottom, and I find the x position is somewhere at the 2 meter mark. Now we need to find y. The same way. Here's your total displacement, mass-weighted positions in the y direction. I said displacement, I meant mass. Sorry. M1, y1, M2, y2. Again, except now we're going to use these y positions over the total mass of 6, and I find 0.5 meters. So this was 2. That's our x center of mass. Here's 1, 2. So right in here, right here, that is going to be your center of mass of the system. So if you just tap this system or bonk it, that's where it's going to rotate around. Let's take a look now when we get to use integrals, because we love integrals. Let's take a look at this uniform rod. And the word uniform has a special meaning. It means that it's constant density. Rho, the symbol we use for density, is mass over volume. Since it's constant, we know that a little piece of mass over a little piece of distance is going to have the same value, which means that we can say that dm, a small piece of mass, is equal to m over L, the density, dx, times a little piece of length. This is going to be very useful because it's easier for us to visualize, at least it's easier for me to visualize, integrating over a position than it is over a small chunk of mass. And now we're going to use integration. It's uniform, so we've got to do this. Where that number on the bottom? Total mass. Good job. Total mass of this rod is just m. We'll use that trick we just talked about to get m over L dx. Those are just constants. And that m's even going to go away. And now I have to integrate x dx and evaluate from 0 to L, being our positions, and you will find out that the x-center of mass is just L over 2, which happens to be right in the middle of this rod, which if you can picture like holding it with your finger, that's where it would balance. And if you just hit the rod, it would spin about its center of mass. In this case, the middle, which makes sense. I like it when physics makes sense. So if you have any questions, please feel free to ask in class, shoot me an email, and I will see you in class. Thank you.